Hello students, in this video we will discuss about LTI system properties in terms of impulse response. Now this belongs to module 3. So whatever we discussed in the previous video, that is the problems on convolution integral is the module 2 ends there only. So in the module 3 we'll be discussing about the properties of LTI system in terms of impulse response. So in this, the very first topic is system interconnection. So the video will take a time, so be patient and go through this video. Okay, so the system interconnection means the LTI system will be connected in series and parallel, and we'll go through what property the LTI system will possess by writing the equivalent system for that, and then we'll go deriving whether it is that is the proof of that. Okay, so first let's take the LTI system in parallel connection. So we say that as parallel connection of LTI systems. Okay, so in this case, let's consider two LTI systems with the impulse response h1 of t and another system with the impulse response h2 of t, which are connected in parallel. Now for these two, the input is the same, that is x of t. Now for this, so we get output y of t here. Okay. Now this we are performing addition here, and the output of the first system we call it as y1 of t, and the second one we call it as y2 of t. Therefore y of t will be y1 of t plus y2 of t. So this is a system with impulse responses h1 of t and h2 of t connected in parallel. Now if we write the equivalent circuit for this, or we can call it as equivalent system. So the equivalent system for the above system will be the sum of two impulses So this is the equivalent system. So let's write it that as equivalent system. So this is the equivalent system for the parallel connection of LTI system. Okay. Now let's see whether we get to that point or not. So how do you define y of t? From the parallel connection, you can call this as figure 1 and this as figure 2. Okay. So in the first figure, you can see the output y of t is equal to sum of y1 of t plus y2 of t, which are the outputs of two respective systems which are connected in parallel. So let's define that one. Y of t is equal to y1 of t plus y2 of t. Okay. So from this, for this input is the same. Now here y1 of t is what? X of t convolved with h1 of t, and y2 of t is x of t convolved with h2 of t. From the figure we can write it like this. So this is convolution of x of t with h1 of t plus x of t convolved with h2 of t. Now, if we elaborate this by using the definition of convolution integral, so this will be tau varying from minus infinity to plus infinity, sorry about that, x of tau h1 of t minus tau d tau plus integral tau varying from minus infinity to plus infinity x of tau h2 of t minus tau d tau. Okay, so this is our y of t. Now, if you observe this above expression, for both the system, x of tau is common input. Okay, so x of tau is common input for both the system. Therefore, the two integrals can be combined. So, we can combine these two integrals because x of tau is a common input for that. So, therefore, y of t. So, y of t becomes integral tau varying from minus infinity to plus infinity x of tau, and these two h1 of t minus tau plus h2 of t minus tau d tau. Okay. So, give some name for the expression, call this as 1 here. Now, if you assume that the overall system impulse function h of t is equal to h1 of t plus h2 of t, then since it is an LTI system, so it possesses time invariant property. So, then h of t minus tau can be written as h1 of t minus tau plus h2 of t minus tau. Now, this one I can replace h of t minus tau by this in equation 1. So, if I do that, then y of t is equal to integral of minus infinity to plus infinity x of tau h of t minus tau deta. So, you might be wondering what is this. So, this h of t represents the overall system impulse function of the system. Okay. Now, this we have expressed as two impulses which are connected in parallel. So, that is why h1 of t plus h2 of t is equal to h of t. So, that is h of t is the impulse response of the equivalent system representing the parallel connection of two systems. Okay. So, that is why h of t is equal to h1 of t plus h2 of t, or you can call it as the overall impulse response of the system. Now, if you observe this y of t, now you can see this is very similar to the expression of our convolution integral. So, we can write it like x of t convolved with h of t. Okay. So, this is where we end our simplification. So, we started this considering the parallel connection, and this is the equivalent system. Okay. So, this equivalent system is for the parallel connection of impulse response, the LTI system expressed in impulse response. Now, from this we get two things. So, first one is h of t, which is identified as the impulse response of equivalent system representing the parallel connection of two systems. So, the impulse response of overall system represented by two LTI systems which are connected in parallel is the sum of their individual impulse responses. So, that means the overall system impulse response is the sum of their individual impulse responses. So, this is what we get when the system is connected in parallel. Now, if you want to say this mathematically we can say that the convolution possess distributive property, that is x of t convolved with h1 of t plus x of t convolved with h2 of t is equal to x of t convolved with h1 of t plus h2 of t. So, how we got here? Here you can see y of t is equal to x of t convolved with h of t. So, what is h of t? We assume that it says that h of t is the overall system impulse response, which is the sum of individual responses of the system. So, based on this, I have replaced h of t with h1 of t plus h2 of t. So, this is what I get here. Now, what is y of t? You can see here it is. Here the y of t, we started with the parallel connection, that is the output of y of t is y1 of t plus y2 of t, which is x of t convolved with h1 of t plus x of t convolved with h2 of t. So, this is y of t. Now, this expression we substituted the values here, and we say that the convolution process, this convolution possesses distributive property. So, that means when two systems are connected in parallel, that is in LTI system, if the systems having impulse responses are connected in parallel, then the system will possess distributive property. So, this one we derived this for a continuous time system. So, similarly, we can write the same for a discrete time system. So, we can write the same for discrete time system as x of n convolved with h1 of n plus x of n convolved with h2 of n is equal to x of n convolved with h1 of n plus h2 of n. So, this is the distributive property the system will possess when it is connected in parallel. Okay. So, this is the first system interconnection property. Now, if the same system, what if the system is connected in cascade, that is series. Now, if you go for cascade connections of LTI system, so consider two systems which are connected in cascade. So, this is the first system for which the input is x of t, and we will get an output. Let us call this as z of t. Then it is connected in series with another system having impulse response h2 of t, and here I get my output of the system y of t. Now, this z of t is an intermediate signal. So, so how do you define y of t? So, y of t now can be defined as, so this for this y of t, the input is z of t. So, z of t convolved with h2 of t. Okay. So, this call this as equation 1 here. I will write the equivalent expression or equivalent system connection in the end after going through the simplification or deriving what it looked like. Now, based on this, we can write this tau is equal to minus infinity to plus infinity z of tau h2 of t minus tau d tau. Now, here you can say z of t is obtained by the convolution of x of t and h1 of t, that is the output of first system. So, what is z of t here? So, z of t is the output of first system. So, therefore, we can express here, since we have z of tau, instead of writing twice, I will just express this in terms of tau only. Z of tau can be written as x of tau convolved with h1 of tau. Okay. Now, if you express this using the convolution integral expression, I will use a different variable here as an integration variable. I will use v. V is equal to minus infinity to plus infinity x of v h1 of tau minus v dv. So, here v represents the integration variable. Okay. So, now let us substitute z of tau in this equation 1. So, let us call this as equation 1, not the previous one. So, if you express this in equation 1, substitute this. So, then what happens to y of t? So, therefore, y of t is equal to integral of, so first one tau varying from minus infinity to plus infinity, and second one v varying from minus infinity to plus infinity x of v h1 of tau minus v and h2 of t minus tau d tau dv or dv d tau. Okay, I can write the one for this one and second one for that. Let's do in the proper way itself. So to avoid the confusion dv d tau. Okay, next I will replace this tau minus v with some other variable. So then I can, if I put, let's eta is equal to tau minus v, then what happens to tau? Tau is equal to v plus eta, I guess. I have to substitute here and I have to change this one. Now what happens here, if you observe, I am replacing tau minus v with the eta, so then tau will be written as v plus n, that is equivalent of that, and I want to interchange the order of integration. So this is the same thing we did in the convolution integral derivation. So interchange the order of integration. I will interchange this because for with respect to this change for eta, this x of v will become constant. So I will take this and dv outside and I will change this to integration, interchange this integration, and I will reiterate the expression after changing the variable tau minus v with eta. Then this tau will be replaced by v plus eta. Okay. Then what happens to y of t? So y of t is equal to integral of v is equal to minus infinity to plus infinity x of v. So this is the first one I have written. Now the second one, since I have replaced this with tau is replaced with another variable, now this will be equal to eta varying from minus infinity to plus infinity h1 of eta h2 of, so here h2 is t minus tau is there, tau is equal to v plus eta is there. I will directly multiply with minus and I will write it here. So that becomes t minus v minus eta d eta dv. So tau is replaced by d eta, and then so this is what we get here. So this, we call this as equation number 2. Okay. So here the inner integral, this one, this inner integral is identified as convolution of h1 of t and h2 of t. That is, these two are identified as or obtained by convoluting h1 of t and h2 of t. So that means this h1 of t and h2 of t are the two individual system impulse responses, but we consider the overall system, it is nothing but our h of t. So h of t is equal to h1 of t convolved with h2 of t. This is what the meaning of that. So these two are considered obtained by the convolution of these two, which is nothing but our overall system impulse response. Okay. Now, if this is the case, how do you define this? So this is defined by minus infinity to plus infinity. Since we have eta here, I will represent as h1 of eta and h2 of t minus eta d eta. So this is what I will get. Okay. Now, this is an LTI system which possesses time invariance property. So whatever the time shift I apply in the input, the same time shift will be the same time shift will be available at the output. So therefore, if this h of t I give a time shifting input, then what happens to this expression? So this expression will become v varying from, sorry, not v, it is eta varying from minus infinity to plus infinity, h1 of eta, h2 of t minus v minus eta d eta. Okay. So this is not n, this is eta. So if you are getting confused, please correct it. This is eta, not n here. Okay. So next, if you observe this, this is the inner integral which is present in equation 2, this one, that I can replace this with h of t minus v. Why I have written v means here we have a term v, so that's why I have expressed the shifting variable as v here. So therefore, equation 2 becomes y of t is equal to integral of v is equal to minus infinity to plus infinity x of v, and this entire term is the inner integral which I will replace this with h of t minus v dv. Call this as equation number 3 here. Now this you can see it is nothing but the convolution integral of x of t and h of t. So we can write it as x of t convolved with h of t. Here the only difference is the integration variable is v here. So that is understood. We can use any variable, we can take any variable as a integration variable. Okay. So this is what we got from the output. That means x of t convolved with h of t, where h of t represents the overall system impulse response. Now what about this impulse response is, it says that the impulse response of the equivalent system. So based on this, we can write the equivalent system in this way: h of t is equal to h1 of t convolved with h2 of t. So this is the equivalent system. Now how we got here? Y means, as if you come to this point, it says the inner integral possessed the integration of the convolution, that is h1 of t and h2 of t. If you convolve these two, then only we get this. So based on this, we have written h of t is equal to h1 of t convolved with h2 of t. So considering this fact, we can say that the impulse response of an equivalent system representing two LTI systems which are connected in cascade is the convolution of their individual impulse responses. Okay. So if a system is connected in cascade, then the overall system impulse response is the convolution of the individual impulse responses. That is the meaning of it. Okay. So now we go further here. We move further. If you see this, z of t is equal to x of t convolved with h1 of t. Why we are moving further means we have not yet come to the conclusion which property this system will possess. So that's why. So z of t is equal to x of t convolved with h1 of t. So this is present in equation 1. If you have doubt, you can go back to this one. Here it is. Okay, from equation 1. Okay, I think I changed this from here, this to this. So here you can see this from the system 1. You can say y of t is z of t convolved with h2 of t. And what is z of t? Z of t is x of t convolved with h1 of t here. I think I have not mentioned any equation. Let's leave that part. So z of t is equal to x of t convolved with h1 of t, which is obtained from the system output. And h of t is what? H of t is equal to h1 of t convolved with h2 of t, which we derived just now. So this is the alternative expression for y of t. So that means in equation 3, if you observe this, call this as 4 here. So in equation 4, you can observe that x of t is convolved with h of t. So this h of t is the overall system function, which is nothing but the convolution of individual impulse responses. So based on this, we can say that the system equation 4 establishes that the convolution possess associative property. How? Let's see this. In the beginning, you can see x of t convolved with h1 of t convolved with h2 of t. So this I got as a system output. How is that? Because y of t is equal to z of t convolved with h2 of t, right? So this is the system output, parallel system output. So based on this, I can write here, you can see z of t is what? X of t convolved with h1 of t whole convolved with h2 of t. So this is obtained from the first connection, that is the system which is connected in cascade. Now at the end here in equation 4, we can see y of t is equal to what? X of t convolved with h of t. So that will be equal to x of t convolved with h of t. Now what is h of t? H of t is the overall system impulse response, which is nothing but the convolution of two individual impulse responses, that is h1 of t convolved with h2 of t. So based on this, we can say that the system possesses associative property. So this is the first thing we got from this property when the system is connected in series or in cascade. Okay. Now the secondly, if you continue further, for a cascade system, we wrote h of t is equal to h1 of t convolved with h2 of t. Now if you express this, tau varying from minus infinity to plus infinity, h1 of tau, h2 of t minus tau d tau. So let v is equal to t minus tau. I am replacing this tau with v. So then what happened to this tau? So then tau will be equal to, I think, v plus t, I guess. Tau will be equal to, yes, tau will be equal to t minus v. Yes, tau will be equal to t minus v. Okay. Then if I replace this, so then what happens to this equation? Integral h of t is equal to minus infinity to plus infinity. This h1 of tau will become h1 of t minus v, and this h2 of V dV. So based on this, we can write this as H2 of T convolved with H1 of T. So that means the convolution can be performed in any order. So if you express this graphically, x of t, h2 of t, h1 of t, y of t. So what does this mean here is the convolution of h1 of t and h2 of t can be performed in either order. That means if you observe equation 5, here you can see x of t convolved with h1 of t whole convolved with h2 of t is equal to x of t convolved with h1 of t convolved with h2 of t, right. Now this is what we took here, h1 of t convolved with h2 of t. So based on this, we can write that the order can be anyone. That means the convolution of this h1 of t convolved with h2 of t. So it is not necessary that the order should be h1 of t here and h2 of t here. So it can be of any order. Then also we will get the same thing as the system output. So the output won't change here. So that means x of t convolved with h1 of t convolved with h2 of t is equal to x of t convolved with h2 of t convolved with h1 of t. The meaning is this: the output of the cascade connection of the LTI system is independent of order in which the systems are connected. So the order is not necessary here. It can be connected in either. The order is not the, if you are connected h1 of t here and h2 of t here, then also you will get the same thing. And if you interchange the order of this h1 of t and h2 of t, so then also the whenever the system connected in cascade, so the order is independent of the system's output. That is what the meaning is. So if we express this mathematically, we say that the mathematically we can say that the convolution possess commutative property. It is h1 of t convolved with h2 of t is equal to h2 of t convolved with h1 of t. Okay. So if you write the same for discrete time system, that is h1 of n convolved with h2 of n will be equal to h2 of n convolved with h1 of n. So if you are messed with this, where we started, why we have ended here is, so I will just brief it once again. So we started with a system having which are connected in cascade here. Now based on this, we got our output y of t as z of t convolved with h2 of t, right? And we came to a conclusion that based on this, the equivalent system will possess the convolution of individual impulse responses. So that is what it means. So that we described here in equivalent system, where the system impulse response, that is the overall system impulse response, possess convolution of individual impulse responses. Okay, so this is the first thing we got from that. And to continue that, we can say that the system, the convolution possess, this convolution possess associative property. How? We took the expression y of t is equal to z of t convolved with h2 of t, where z of t is equal to x of t convolved with H1 of t. We substituted this and we came to the conclusion that, so to the RHS we got this one, and to the LHS we just substituted the respective expression here. So y of t is equal to z of t convolved with s of t. Also y of t is equal to x of t convolved with h of t. So this is the equivalent system for the cascade connection that we obtained. So second thing, this is the first thing from the cascade connection, we say that it possesses associative property. Now we took the fact that h of t is the convolution of individual impulse responses. So it is not necessary that the order should be like h1 of t convolved with h2 of t. So you can see that here we represented the system cascade connection h1 of t convolved with h2 of t. Even if you interchange this order, then also the system will be, output will be the same. To prove that, we elaborated this further and we came to this conclusion that the system will possess commutative property. How means, we just took only the impulse response here and the convolution of h1 of t, h2 of t, just replace this time shifting with some other variable, and we see that the system possess commutative property. So from that property we can say that the RHS, you can see this part, the RHS, it means this x of t can be, this order can be interchanged, then also there is no change in the output of the system. So that is the second thing we got that. So mathematically saying that the system, the convolution, when the system is connected in cascade, so the order is independent. The system, LTI system, is independent of the order in which the systems are connected. So that is the meaning of it. So hope you have understood this concept, and in the next video I'll take some examples on this system interconnection. Okay. So if you have any queries, do reply or comment on this video. Thank you.